Welcome. Today we're talking about operations with scientific notation. So we already know how to put numbers into scientific notation. We already know how to take numbers out of scientific notation and put them in standard form. But we also need to know sometimes you got to multiply or divide or add or subtract numbers that are already in scientific notation. And if you don't want to change them to standard form, like we usually add or subtract or multiply or divide numbers, you can actually do some shortcuts instead of using those really big numbers or really small numbers. So let's check it out. The notes you need to know are that the associative property allows us to ignore or rearrange parentheses when we are only multiplying. So, this is going to be useful because scientific notation includes multiplication pretty naturally. So this tells us that even if things are grouped together, as long as you're only multiplying, we're allowed to kind of ignore the parentheses or change them around if we want. Same with the second note. It says the commutative property allows us to rearrange numbers when we are only multiplying. So not just the parentheses we can move around, but we can move around the numbers. So with those two together, we can pretty much, if we're multiplying, multiply in any order we want. And then the last note is that the distributive property allows us to multiply add-ins by the same number individually or after adding. So what that's saying is, like, if you have 3 times x plus 5, you can multiply 3 times x and then add 3 times 5. Or you can add x plus 5 if you find out what that value is, and then multiply by 3. So you can either put them together first, after adding, you can multiply, or you can multiply the numbers individually. So this is something we're also going to use on the next page. So let's check it out. The first example we have is 3 85/100 times 10 to the 18th power divided by 1 1/10 times 10 to the negative 12th power. Now, some of you are probably thinking that, oh, if we're multiplying by 10 to the negative 12th power, I could turn that exponent positive by flipping it up top to the top side of the fraction bar. And then we'll be multiplying two numbers in scientific notation. And that would work. That would be fine. But I'm going to do it a different way just to try and explain how to divide when you have two numbers in scientific notation. So let me get a pencil, and I'm going to try my best to make this neat, but no promises. So here we go. And you might also be wondering why you said we can rearrange the multiplication. We can multiply the numbers in whatever order we want. You didn't say anything about division. But if you know that when you're dividing, you can always rewrite it as multiplying by the reciprocal. So that's what we're going to kind of imagine here, is that we're multiplying each of these by the reciprocal instead of dividing by them. So now we'll say, well, which ones do we want to pair together? Well, I like 3 85/100 and 1 1/10. I know how to divide those pretty easily. So let's try it out. So we'll do 3 85/100. That is our dividend. And we'll be dividing by 1 1/10. That is our divisor because it goes on the outside. It's attacking the house. But when I divide decimals, I like to swoop it so that I can be dealing with a whole number divisor. So in this case, we'd have 38 5/10. This is in blue right now, but it needs to be taken down. You need to show your work as well. So make sure that you're copying this down with me. 11 goes into 38 3 times. I kind of gave it away there, and it's 33, but you knew that. When we subtract, you get 5. Then we can bring down another 5, and I know that 11 goes into 55 5 times. And I'll bring my decimal up. So we know that when we divide these two, our answer, or part of our answer, is going to be 3 5/10. That's great. But we still need to do something with these powers of 10 that we're using. Luckily, we know something about similar bases, or the same bases with different exponents. If we're dividing the same base with different exponents, you're allowed to subtract the exponents because they cancel out top and bottom. And that's the reason. We don't like to just memorize rules. We like to know the reason. So 18 minus negative 12. We can subtract. So if we're going to subtract negative 12, 18 minus negative 12, that's actually plus positive 12. That would give us 10 to the 30th power. And so you students that are watchers out there who thought, oh, we could flip this to the top and it would become positive, well, that makes sense too, because then you'd be adding positive 18 and positive 12 because you'd be multiplying them on the same side of the fraction bar. So you get the same answer either way, and it is right here. And you can see how that was probably a little bit easier than writing out this big number up top and then dividing by an extremely small number down bottom because of this negative exponent. Okay, let's look at another example. Gemma's heart has 4 54/100 times 10 to the 10 to the 9th power cells, and a Meg's heart has 9.8 times 10 to the 9th power cells. How many cells do their hearts have total? Well, let's check it out. So in this case, we're going to be adding, so I know that we're adding 4 and 54 hundredths times 4.54 times 10 to the 9th with 9 and 8 tenths times 10 to the 9th. So it's funny we're talking about Gemma, because if we're following the order of operations, I know I need to multiply this one and I need to multiply this one before I can do the addition. However, the distributive property tells us that if we're multiplying two numbers by the same thing and then adding them, well, I can add them first and then multiply by that number once I find the sum. I can just sum them and then multiply rather than multiplying them individually. So let's do that actually. So we're going to multiply by 10 to the 9th, but first I'm going to add 4. Squeeze it in. Oh my gosh, this looks awful, but you can understand it, I hope. Times 9 to the 9 and 8 tenths. So we're going to add them, and then I know that I'm just going to be multiplying times 10 to the 9th power. So let's do this. Let's do it mentally. You know, why not? So in the hundredths place, if I add 0 hundredths here, there are no hundredths. 0 hundredths with 4 hundredths, that'd be 4 hundredths. If I add 8 tenths with 5 tenths, I'll have 13 tenths, and that actually leaves me with 3 tenths. And then the group of 10 tenths translates into a 1. And then I have this little 1 that I carried, plus 9 is 10, plus the 4 ones over here, that'd be 14 ones. 14 ones times 10 to the 9th. But this is no longer in scientific notation, because in scientific notation we know that we need the first number to be between 1 and 10, and 14 is certainly bigger. So I'm going to move that decimal over one more time, and we'll have 1.434, but it's no longer 10 to the 9th, because to have the same value as this expresses, I'm not going to move the decimal 9 times from here and be equal to moving the decimal 9 times from here. I need to move it one more time to the right. So in this expression, we're moving the decimal at trading place values, but the decimal is kind of moving 9 times to the right. In this case, it needs to move one more to get back to the original spot, so we're multiplying by 10 to the 10th power. And this is how many cells. Boom, baby. That's how many cells their hearts have total. Cool. I am going to show you the problems I would like you to do on your own. So let's check that out. The first, I know there's a clear ink button. I'm sorry, Renato. This is a great program. Bad video. So let's check it out. On this last one, I want you to do these problems by yourself. Check them out. The first one is 2 and 38 hundredths times 10 to the 14th power minus 1 and 1/10 times 10 to the 14th power. Think about what property you could use so that you don't have to write out all those zeros and then subtract. Try and do it by organizing things in a way that makes more sense. Number 2 says the human body hosts about 1.2 times 10 to the 13th bacteria cells. That's a big number of bacteria cells because they're really small. If each cell has a mass of about 9.5 times 10 to the negative 15th, ooh, that should be kilograms. That's how many kilograms. I looked this up because I want these to be, useful questions, not just fun questions, or not just annoying questions. Kilograms, and how much mass of bacteria does a human body have on average? We're just talking about just one example. But I want you to think about that. Think about what operation. If each bacteria cell has 9.5 times 10 to the negative 15th, and there are very many bacteria cells, what can you do with those numbers to try and find out the total mass of bacteria cells? I'll leave you to that. Use the examples we went through for help, and use those properties, and I'll see you later.